Okay, we're going to start. Let's just punch out one of these chapters. Let's do both of these here for the end of the solutions chapter, which falls in sort of the colligative area. There's two formulas and two separate sort of problems that you might encounter. One is the osmotic pressure. That's basically the ideal gas law, but written in a different form. And then there's the freezing point depression or boiling point elevation. The way I do it in my class is just to write one for, I combine the two formulas into one. Okay, so let's talk about how these work. Osmotic pressure. The pi just means osmotic pressure, so it's pressure equals I. We'll talk about that in a second. Molarity, R. Make sure you get the right R. Because of the units, the liters here, and the atmospheres that would be here, you need the normal ideal gas law constant. I'll give you both R's on the test. You'll need to pick the right one on the back page. Okay, and then T, temperature in Kelvin. Same as the ideal gas law. We'll go over I in just a second. Over here, this is the change in temperature, whether that's depression from the freezing point or elevation from the boiling point. Either way, that's that. Okay, this is a constant. That has to be given. And this is the molality. I'll put molal for molality. Okay, let's talk about I, and then I'll say a little bit about both these formulas. Okay, I is basically the number of entities in solution given by the solute. So for example, anything that's an electrolyte that separates out, whenever it separates out, that will make essentially a new entity which will affect both of these. So for example, all organics or moleculars, I will equal 1. They don't separate out in solution. They're not good electrolytes. But things that are good electrolytes would be aqueous salts, like sodium chloride. There's a sodium and a chlorine, so that'll count as 2. Or aluminum chloride. There's 3 chlorines and 1 aluminum. That as an aqueous salt will separate out in solution. That'll give it I equals 4. So each entity that is provided, and the number is only bigger than 1 when it's aqueous ionic compound. An ionic compound is anything with a metal and a non-metal. Okay, so you gotta get the right I. A lot of times they're organics, sugar, moleculars, things like that. Those are all I equals 1. They're not good electrolytes. Okay, so I, that's the same I in both formulas. Let's talk about the second formula just for a moment. Let's go scratch here. Let's say you're putting salt in a container that has water. Okay? The K value, the K for the right-hand side formula, is for what compound? Water or salt? Water. That's right. It's always for the solvents. When you're determining the freezing point depression or the boiling point elevation, is that for water or salt? Also water. So it's how the solute, salt, changes the solvent. Okay? So what there is more of, water will go with the K value, and it will be the delta T for the water itself. The I value is really associated with which one? Salt or water? The salt. Okay? The molality is moles of what in the numerator? Salt over kilograms of water. So that includes both. The molality would be moles of the solute divided by the kilograms of the water. Okay, good, we clarified that. So make sure you know which constant to use in case you're given multiple constants. All right, other thing that I want to talk about here, usually these are plug and chug. There's nothing else, but you got the numbers, you plug them in, You get the answer. Just straight up use the formula. That would be kind of like the medium or medium easy version of the question. Yes?
For the molarity of the osmotic pressure, that's for the molarity of the solid.
Yeah, for the molarity, just to clarify, question over on this side, that's the moles of, if we have this solution, moles of, in the numerator, salt, over liters of the whole solution, which if there's very little salt would just be the water. Yeah, okay, good, thanks for clarifying. Temperature would be of the whole thing, the R is just a constant. So these questions I was asking about, this one less apply over here. Okay, two types of questions. One, straight up plug and chug. Just give you, and you'll know what kind of problem it is. You'll either see the word osmotic pressure, or something really similar to that, or osmosis, etc. Or you'll see something about a freezing point, or a melting point, or boiling point going up or down. So it should be really clear from the words which type of question it is. How do we make these harder? Is inside the molarity for the first one, or the molality for the second one, we ask you about the following. We could ask you about the mass of the solute or solvent, the moles of the solute or solvent. We can ask you about the molar mass of the solute or solvent. And sort of connected to that, we can also ask you about the molecular formula. So if those seem a little fuzzy, I did questions on the harder, so this second one, not straight up plug and chug, but you solve for molarity or molality, and then you go to what you want. I did a couple of those examples in lecture when we did those. If you have a specific question when we get to the second half, for sure ask me. But this would be the harder version of the question. It doesn't get harder than this though. Okay, so where again, we give you all the data, you would say solve for molality, and then convert molality to whatever we ask for. Okay, so that's my little summary of that one. Another common question I ask conceptually, you'll often see some conceptual questions in the multiple choice related, especially to the second one. If I wanted to lower the boiling point of water, what would I do? Would I add a solute? Would that do it? No. Adding a solute would not lower the boiling point of water. It would do what? Raise it. What if I add more water? Would that lower the boiling point? No. There's no way I'm going to lower the boiling point of water. You can only raise it. Is that okay? People sometimes get confused and they think the boiling point is going down. It's not. Neither is the freezing point going up. That one only goes down no matter what you add or whatever. Okay. Next. So we did both of those. Let's go over to this side. We can punch this out really fast too. The common ion and the buffer. So this is the section of my class that we just started. First, a little review of the common ion. Let's say we have a molecule, sodium cyanide. Is this a good one? I'm trying to think if this is a good example. No, I don't like that one. Let's say we have a hydrogen cyanide plus water. Let's write the general equation for an acid, or the acid hydrolysis, acid ionization. That would be Cn minus plus H3O plus. Okay, so we have this. If I add something like sodium cyanide, and let's say it's a solid, I can put this in solution and it'll dissolve in water. This will dissolve 100%. It's aqueous, it's a good electrolyte. Well, like you learned in 2A, good electrolytes totally separate out in solution to Na plus Cn minus. If I had to label Na plus, what is that? Spectator ion, and in terms of pH, we would say it's neutral or 7. So, does it have any effect? Nah, no effect whatsoever. It is the conjugate of a strong, specifically sodium hydroxide. Any conjugate of a strong is neutral. Okay, so make sure you got that down. So this plays zero role in what we're thinking about right now. Okay, now the cyanide though, that one's important. This cyanide right here, once I add this, then we're producing now more of this one here. It'll cause the top reaction to shift right or left? Left. So once I add the sodium cyanide, that's more cyanide ion, that shifts the top one to the left. And I'm going to then increase or decrease my H3O plus concentration. Yeah, if that shifts to the left, that will go down, and pH will go what? Up or down? Up. So if I'm losing H3O plus, it's going down, the pH has to go up. So it's getting more acidic or more basic? More basic. That's the common ion effect. Okay? Common ion, literally, I've added the common ion, and it raised the pH. Okay, I'm adding the common. Let's see if that makes sense in another realm. So side kind of topic. Take a look at only NaCN in aqueous solution. Okay, you told me this part was neutral. And then you might be thinking about the other part, the CN minus. So we already figured out the first part. The conjugate of CN minus is HCN. What is that? Acid, base, neutral? Acid. Strong or weak? Weak. So let's get a different color here. This is a normal acid, a normal weak acid. So this is a normal base. So this is a base or basic. Either way, fine. So that is a base. So it would make sense if I add the second one, sodium cyanide, into solution and it's a base, the pH better go up. Right? If I'm adding a base, that's the only thing that could happen. So again, one more time. I added a base. Through the common ion effect, we realized that the pH will go up. And through what we knew from before, if I add a base, which this is, we just figured that out, the pH better go up. So this is consistent with other things we learned. That's the common ion effect. How that affects the ice table, I'll just do this quickly. You're going to take the original reaction. If you do an ice table, and let me just show you the setup. It affects very little, but one little tiny piece of the ice table. Ignore this. If you have, let's say, a molarity that's given here, let's say molarity X. I don't know what else to label it. This will be 0, but this, because of the common ion, will be some molarity they'll have to give you, and I'll just call it molarity Y. It's some value that is given. So both the molarities are given. This must shift which way, right or left? The right. Because it has to go towards this 0, right there. Right there, make this huge arrow. Has to go towards the 0. It cannot go backwards, there's no product. It'd be impossible. So this would be mx minus x. This would be my plus y, no plus x, sorry, and this is x. So then you set up, everything's normal. The only thing that's going to be different is now you have a molarity in that cyanide column, which is the common ion column. It's the thing that you added originally, which was this. Zoom out a little bit. We added this, and that puts that number here. So because of this, I'll circle it in green, this number appears in the ice table. That number previous to common ion knowledge was a 0. All right, so that's a common ion. Let's also talk about buffers if there's no questions about this. Yes, I see you. Yes. Ooh, I like where you're going. You're going to allow me to cancel out another thing here. When can you ignore X? When was that? Here. Okay, so side topic, other chapter now. When can you ignore X? Right here, you can. Let me tell you why in a second, but yes, these kind of problems, you can. There's a couple ways you can explain that. In general, because that's a weak acid, you can. X is going to be assumed as small because this reaction will shift forward, but not very much. So this X, there will be a plus X over here on the right, but it's super tiny. Okay. So, yes, you can assume it's small, but I'm more technical way of doing it, or a more numerical, quantitative way, would be to say whether you take mx or my, it doesn't matter, either of those values, whichever one's smaller, you divide that by the Ka of HCN, and that better be greater than, yeah, the number 100. That's just an easy assumption to check. If that's true, it's going to be totally fine. I usually do this in my head, but you can write it down, whatever's easiest for you. Yeah?
In the textbook, some of the answers drop the X even when that was like 41.
So in the textbook, they're saying if this wasn't exactly 100, it was less than 100, maybe in the 40s, the textbook dropped the X. That's actually allowed. Basically, the smaller that number is, the more error you're going to have in your answer. So it depends how much error you're okay with. So we're using, say, the 5% rule. That's a totally arbitrary number. You could use the 10% rule. And then you're just adding more error because of your assumption. So you could be adding, 5 to 10% of error. So the book might have more leeway. I just randomly pick 5%, and then randomly this is 100. It's just a rule of thumb. You can use what the grader uses. Yeah, we're going to use 100, but we're going to make sure, I'll make sure on the test it's really clear. It's not going to be ambiguous. Yeah. Okay, so that hopefully answered your question. I'll get back to the 5% rule more later. But let me mention that since we're on it. In my reader, this is the end of chapter 15, the acid-base chapter. I showed you this at the end of class last time. I just want to point it out one more time. This is on page 87. I'll zoom in on it. Okay. Oops. There. All right. If you see the K summary, what K values are small, all of those numbers are small, and that's related to the last thing on the list. What K values will cause X to be small? This is what was asked. It's sort of asked. I would think of it this way. You got a weak acid or a weak base, it's probably going to work as a rule of thumb. You can use the check that I just did to numerically check that, but if you're in one of those types of problems, it should be fine. Okay. Cool. All right, so that's the X is small. Let's get back to buffers now. Or that section we were talking about buffers. All right, for buffers, we haven't quite done this in class, so this is a little bit ahead. But a buffer has a couple parts that are significant. First, you need to have a weak acid plus its conjugate weak base, or vice versa. A weak base and its conjugate weak acid. So you need a pair that are weak. Second thing, they need to be, these two need to be of similar molarity. So they can't.
Can you quantify that?
What's similar mean? So similar means probably within a factor of 10. Again, this is a rule of thumb. The closer the molarities are, let's say one's 1.0 and the other's 1.1, that's great. The better the buffer will work. The further apart they are, let's say one's 1 molar, another one's 0.1 molar, the worse the buffer will work. So the more similar the molarity, the better the buffer will work. And then relatively large, you're not going to like this one either, volumes. Meaning, if the buffer is something that resists pH change, so anything you add to it can't be of large volume. The larger the volume of the thing you're adding to the buffer, the more you will likely destroy the buffer. But if the buffer is of large volume, numerically, then you add something to it of small volume, the buffer will work in the most effective way possible. Okay, so there's no particular number, but in general, you'd want a relatively large volume. Okay? So how do you identify a buffer? If I give you something like, sometimes it will just be working with the top one right here, or the first two in a typical identification problem. Okay, so the first one's the most important in your typical question of just identifying the buffer. And the second one's probably the second most important in an average problem. So let's say we had HCN. We saw this one just a moment ago. You'd want to ask yourself, do I see an acid in its conjugate or vice versa? Yes or no? Yeah. Acid, conjugate. I'm ignoring the sodium. Why? Spectator, it's a conjugate, it's strong, we don't care about it. Ridiculous. Okay, this would be a good buffer. Okay, given that those two have similar molarities and are relatively of large volume. Okay, let's try another one. Yeah, yes, this is a great one. How about that one? Nope. Why not? These conjugates. First thing, are they conjugates? Definitely. You got an acid and its conjugate base. Okay, what's the problem though? They're strong. This is strong. That's neutral. So this is yes, that's no. Okay, you got the weak. It's got to be weak or it doesn't work as a buffer. Strong acids or strong bases are not good buffers. Okay. Then sometimes we'll put molarities in there. You know, like say this is 0.1 molar, this is 0.5 molar, that's fine. That's close enough. Within a factor of 10, totally fine. Okay. Now, sometimes we like to be tricksy like a fox, and we'll do something like this. Is that a buffer? Yeah, you would think it's not, but that's why I wrote it down. Okay. So HCl, HCl, that's just H3O plus. Is that okay? It's just a strong acid. So, okay. So notice these two react. That's a base, that's an acid. Let's react them. Because this is strong, this one's strong, that I just squiggly underlined, this will go 100% forward. All strong acids or strong bases push the reaction forward completely. The acid, the base will grab a proton from the acid will lose a proton. You get this. We start with 1.0 of this and 0.5 of this and 0 and 0. Is that okay? Now initially that's the molarities we had. But we know the reaction is going to react and it's going to go forward 100%. We're going to lose all of this. It's the limiting reactant. It's the one we have released of. So we're going to lose that equal amount on both sides, the 1-to-1 molar ratio. We're going to gain it over here. So at the end, we'll have 0.5 molar, 0 molar, 0.5 molar, and 0.5. Is that a buffer? Yeah, we have two of equal molarities, a base and its conjugate acid. So I generated a buffer. So yes, it's a buffer. Check. That's a buffer for sure. This will happen. Let's zoom out a little bit. This will happen. There's something in the reader about that when we get to buffers. Whenever you add a strong that is approximately half the molarity of a weak, it will generate a buffer just like this. That's the tricksy version. Okay? All right, first time you've seen it, so it's weirder. We're going to do it in class, because I need to trick everybody. Yeah? Yeah, we don't care about this. This is not an ice table. I will give it a name when we get on Monday. And this is specifically called a stoichiometric table. We're doing stoichiometry. So not an ice table. That's why you saw I didn't label it ice here. The start, middle, and yeah, not ice. Okay, a lot of mumbling. I'll assume that's good mumbling. All right, we started it. Let's continue it. 5% rule. Again, 5%, as was asked earlier, totally arbitrary. And where is this in the reader, just so I can refer to it here? This is on page 76 and 77. So the 5% rule says this. If you take the X value and you divide it by the concentration, I'll just put initial concentration of the acid or base. This is the X value that you're solving for, so it represents the change or shift to equal, to get to equilibrium. If that's true, the assumption works. 5 is arbitrary. It can be larger than that. But the larger you make the number on the left, the more error you introduce into the problem. So 5% is generally accepted. Now the nice thing about this is that this part right here is equal to what's called the percent ionization. Is that for a weak acid or weak base, do I expect the percent ionization to be large or small? Small, meaning it doesn't ionize, it doesn't give protons easily, it's weak. So this number is usually less than 5. That's the 5% rule. But it can get up to 10. This is a function of the molarity, or the initial concentration. As the initial concentration goes up, it drives the percent ionization up. All right, so what kind of questions can we ask of this? I think it would be best if I pause there and do a little bit of weak acid, weak base pH, and that'll allow me to tell you what kinds of questions we can ask for percent ionization. So I'll come back to this, bubble that for a moment, table it, and let's get over to weak acid, weak base pH. Who asked this question? I don't remember. Yeah, do you like acids or bases?
Acids.
Sure, why not?
Okay.
Is there a particular acid you like, or should I just pick one of my favorites?
Whatever you want.
Whatever I like. Sweet. Okay. I don't. I'm not that weird. But let's take this one. This is called what? By the way, what's the name of it? Nitrous acid, yeah. How do I know it's weak? It's not on that table of salts. Yeah, good. Okay. Let's say I knew this was 1.0 molar, just for argument's sake. Let's write the general equation for an acid. We're going to find the pH of this. Okay? pH. First thing you do, write the reaction. So the acid loses a proton, the base gains a proton, and we're going to write the ice table here. This is all to find the pH. It's a weak acid, so I know I must use the ice table. All right, so I ignore water. This is 0 and 0. Remember, if this was a common ion problem, that would be a non-zero number right here. But we're not doing common ion, just to remind you what we just talked about. There's a number here that's not 0 if it's a common ion. All right, this has to shift which way, right or left? To the right. I'll put a plus here, minus here. It has to go to the right. Q is 0, and it can only go right. There's nothing here. 1 minus x, x, and x. I should look up the Ka value. Where would I find that? Back of the test. If you're taking my class, I give you what's on the test in the practice exam reader, and this is one of the tables that's there. I hope I picked one that's in here. Right here. Sweet. It's 7.2 times 10 to the minus 4. So, By the way, for my test, there's going to be several times you do need to refer to that table. So I would, whatever class you're in, get familiar with whatever table you're going to get on the test, because you want to say, oh yeah, I remember seeing hydrozoic acid, you know, on this table, and we read it, you're like, shoot, let me go over here. You get a free equation, you get decay, all kinds of goodies. You're welcome. So, products over reactants, x times x, products, reactants, 1 minus x, all from the I line of the ice table. That is equal to x squared over 1 minus x. What will I do next? Drop the bottom x. Wherever there's addition or subtraction including an x, I'm going to do that. In my head, you can do it written out if you prefer. I'm saying what's 1 divided by this, is that greater than 100? Yeah, crazy greater than 100. It'd be 1,000. So if the initial molarity divided by K is greater than 100, you're going to have a great assumption. That'll be great. Okay, X is going to be tiny. So, X over 1, X squared over 1 is 7.2 times 10 to the minus 4. X is just be the square root of 1 times this number. Okay, anybody got that? What is it? 0.68?
0.0268.
Is that what you said? Okay, you can double check your assumption just in your head right now. Is that smaller than that? Yep. Looks like it's going to be great. That was a great assumption. It's tiny. I'm introducing a 2.68% error, essentially. So I'm okay with that. Close enough. Okay. So that's X. This isn't equal to the H3O plus concentration. I knew that if you zoom out a little bit. Because X is equal to H3O plus, and that's X. So it's equal to that. I can find the pH. pH is the negative log of H3O plus, or 0.0268. Math savant there in the middle. What's this number? 1.57. All right. pH. What else was going to? Oh, there's a pH. That's what I wanted to know. Let's do the percent ionization now. That's going to equal 100% times X divided by the initial molarity. That's going to equal to, as I said earlier, I'm the savant now, 2.68%. So this is less than 5%. 5% rule holds, and this is dissociating 2.68%. Okay? Let me pause for a second, and I have a little more to say, but is there any questions about this at the moment? Very typical problem. I'd expect you to be able to pull this sort of thing off. Yeah?
Wouldn't the pH be too small for
Yeah, the question is, the pH too small? Yeah, it's getting, I mean, it's stronger for sure. Just a general rule of thumb. You gotta remember, the smaller the number, the stronger it is for sure. But because that number is a function of concentration, meaning as the concentration goes up, the pH will go down. Yes, it can get in that range. For a weak acid, at high concentration, it can go to low pH. But it's not necessarily strong. A strong acid, at very low concentration, would easily be that. Does that kind of make sense? So it's a, and pH, remember, because it's log base, base 10, each pH unit is times 10. So pH 0 is 10 times stronger than pH 1. And pH 2, pH 1 is 10 times stronger than 2 because of the base 10. So there's a lot of factors in play. So in class I said, yeah, it's about 0, 1, or 2 is probably strong, but you got to weigh these factors. That's just a rule of thumb. Good. Yes?
If we
When would you have to use a quadratic formula? Let's go back. I'm going to refer to that page in the reader we were looking at a little bit ago. Let me see if I can find it quickly. So I'm going to cover this. I'll put it back right here. When would you use a quadratic formula? Most likely in that third scenario there. It's just a generic KP or KC problem. That's where you use the quadratic. I'll ask everybody, how about the second scenario when K values are large? Would you use a quadratic there? No, that is not an ice table problem at all. That's just straight up, the concentration is the H3O plus concentration or what have you. So it's really that third category there. Not really dealing with acids and bases. Or if the acid happens to be in the middle, which would be extremely rare. Yeah. So for the reader, the chapter 14 or the equilibrium chapter problems is when you probably have to use the quadratic. One more thing. A hard version of this problem would be to give you this number. By paying attention? Well, you don't have to, so here. Give you this number and ask you for this number. I give you this and you go backwards to that number.
We still couldn't see it.
You're welcome. It's a pretty common question. It's in the homework. Yeah, so check out the homework. You should have done one like that. I put it there on purpose. It doesn't show up, you know, it shows up occasionally on a test or a final lab. Yeah. So, next. Let me finish pH then. pH. When you're finding pH, then I'm going to separate this into two categories. The weak acid, weak base category is where you use ice table. And then the strong acid, strong base category, this is where you just use the formulas. I'll write in brown here. Any one of these formulas, pH is negative log, H3O plus, POH is negative log of OH minus, pH plus POH is 14, or H3O plus times OH minus is 10 to the minus 14. Sorry, that's a minus 14 there. Any one of these formulas come directly from the strong acid, strong base. A weak acid or weak base problem would use the ice table, but then when you go to pH, you have to combo it with one of the formulas down here. So most likely you'll use this one if I ask for pH, because from the ice table, you'll get the H3O plus concentration. If it's a base formula, you'll get the OH, so then you'll use a combination of whatever to get to pH. So the weak acid, weak base does use what's written in brown as well, but the strong acid, strong base only uses what's written in brown to get to pH. Okay? So this is ice table plus these, and strong acid, strong base is just these. So that's what I would say about pH. Yes?
Is that 10 to the negative 14 for H3O? But is it just what the pH or the POH is? Is that what you're saying?
This number right here?
Yeah.
That's KW.
Okay.
That's a constant. Somebody asked me about KW. I'll cross that off too. KW is just a constant, but all Ks, somebody else asked me about temperature, I'll cross that off too. All Ks and Q would essentially be a function of temperature, but we really would focus on K. I guess there's a type of problem we could ask you about Q, but generally K is a function of temperature. And so we did the one problem where we had the KW equation. I changed the temperature, and that caused the pH to change. So yes, temperature will change this constant. That only works at room temperature, and that's it. Okay? If it changed temperature, I'd have to give you the new KW. That's kind of annoying on the test, so generally I would keep it at room temperature. Okay, unless it's a very specific problem we're doing about temperature. So, if the reaction is endothermic and I increase temperature, which way does it shift? Endothermic, increase temperature. Shifts to the right, because endothermic means heat is in the reactants. It shifts right. If it goes more to the right now in new equilibrium, K just went up or down? Up. K just went up with an increase in temperature for an endothermic reaction. Opposite if it's exothermic. So it's kind of a logic. Any questions on that? Yes?
And the K goes up because it increases the of the product?
Why does the K go up in that last example?
Yeah.
Because it's going to the right. If it's shifting to the right, there's more products.
Okay.
At that new, now constant temperature,
Okay.
presumably. Yeah. Cool. I just knocked out like 5 topics right there. Yes. Thank goodness. Checked out those. That. Okay, I could probably do one last topic. Anybody have a strong vote? Polly? Yeah, your name? Polly, you were named after polyprotics. That's encouraging. Or you can name your kid Polly. Lots of polyprotic acids. There's more than one proton to give. What you want to remember is that the Ka1 is going to be a lot greater than Ka2. And if there's a Ka3 or more, the 2 is much, much greater than 3, etc. If you're solving one of these for pH, do you use an ice table? Yes or no? It depends on what? Is it strong or not? If it's strong, no. We never use the ice table with something strong. The example here is H2SO4. No ice table. No. Some students will use the ice table to solve problems that are not even acid-base on the exams. I don't know why. You're going to use the ice table if it's anything weak, though. Any polyprotic that's weak, we'll use an ice table. Also, I told you that Ka2 is equal to what concentration?
The second one, or after the second.
Yeah, the species that lost a proton. So that would be, oh, sorry, 2. K2 is equal to the species that lost a proton. No, lost 2 protons. Is that what I said? A2. Jump into 2 there? That's fine. Yeah, so I give this example. Where did we do polyprotic in the reader? Look over there. We did this on page 78 and 79. So for example, let's do a different color. For the species I listed, that would be SO4 2 minus, or HPO4 2 minus, or CO3 2 minus, all those kind of things. They lost 2. Okay? For a polyprotic, the pH comes primarily from which loss of the proton? First, second, third? First decides the pH. If you're doing an ice table for a weak polyprotic acid, you're doing an ice table and you solve it for Ka1, do you need to do a second ice table for Ka2? No. How about K3? No, not again. Just the first velocity of the proton uses the isotope. Yeah.
Would the K3 be equal to species element?
Would the K3 be equal to species of loss 3? No. Nothing special with K3. Yeah, only K2 has something special with it. Okay. How do I determine K? You have to write the equilibrium expression. Okay, I'm going to have a cookie.